Spin Robotics talk series. I am Kostas Daniilidis, and I'm the faculty host for today's talk, together with Pratik Chodari. As a quick reminder, all our talks can be found on our YouTube channel and website. If you're joining us via Zoom, submit your questions at the Q&A. If you're here in person, we have an opportunity to provide your questions to the panelists. This is Stefanos Pertigiozoglou and Yinshuang Zhu. Very glad to introduce to you Professor Tess Smidt. She's Assistant Professor of Electrical Engineering and Computer Science at MIT. She has earned her Bachelor in Physics from MIT and her PhD in Physics as well from Berkeley. And her research focuses on machine learning that incorporates physical and geometric constraints. She has been also the Alvarez Postdoctoral Fellow at the Lawrence Berkeley National Laboratory, where she also developed one of the pretty much the first tensor field network, and also I think she is the most prominent equivariance person, at least in this side of the ocean. I remember in 2018, as soon as the tensor field networks paper came out, we discussed it in our reading group, and it was a real eye-opener that we don't actually until then we used only scalars like RGB or scalar channels, and using vectors and matrices and higher order tensors for symmetry. It would really open for us a huge actually avenue for research. And I would like to say, in addition to pioneering papers, Tess also together with the group of Amsterdam is really providing for us the easiest and to use equivariant library, the E3NN, and thank you very much for that. Today she's going to talk about Euclidean neural networks for learning from physical systems. Thank you, Tess.
Thank you so much. Thank you for the introduction. Thank you for having me. I was super excited to come here and speak with you. I've changed my talk slightly. I've changed the title. A lot of the content is the same, but I hoped to frame it maybe in a way that would resonate more with this audience. So for those of you, especially for those of you who have computers out or online, if you would like to have my slides, they're here at this tiny URL. So it's just tinyurl.com/test-grasp-2024. So those slides are available to you. And I have like links to references. So instead of you having to jot things down, you can just click on the link. Is it possible for people to ask questions during the talk? Wonderful. Okay, that is definitely my preference, especially because some of these details, some of the technical details, I would much rather correct anything that I'm saying or clarify anything that I'm saying as we're going along. So please feel free to ask questions. I'm very happy to answer them. So here's a bit of an agenda for this talk. So first, I really want to discuss the trouble with machine learning and using coordinates and coordinate systems. So what is inherently problematic about doing sort of traditional machine learning with coordinates. And this is to motivate why we may want to include Euclidean symmetry, if we're in 3D space, 3D Euclidean symmetry into our models. And then if we do that, what are some of the properties and how, at a high level, how do we actually go about doing that at the network operation level? And then I'm going to talk about some applications just to show that Euclidean neural networks are a class of networks. They're not a specific architecture. And so I'll talk about some Euclidean neural networks that we use for things like regression in the case of properties that we use for molecular dynamics. Then I'll move on to some generation tasks, so generating molecules or learning rich representations of proteins. And then a little bit of kind of maybe more oddball things you can do with these networks because of the rigorous guarantees that they're built from. So like rigorous like hypothesis testing, such as finding symmetry breaking in data sets or in dynamics. So with that said, let's get going. Okay, so hopefully this is a non-controversial statement that coordinate systems are useful for describing physical systems. So we use them to describe where things are in 3D space, how they're oriented, such as this robot arm and maybe a teddy bear that we would like to grab. We also use coordinate systems to articulate directional properties of physical systems. So these could be things like vectors, which are forces or displacements, 3x3 matrices, such as moment of inertia tensors, stress strain tensors, 3x3 tensors. So the only one I could easily come up with is the Levi-Civita tensor, which encodes basically cross products and anti-symmetry, and even higher ranked tensors like elasticity tensors. So tensors use coordinate systems to articulate directionality. And we can also define these tensor fields over space, whether it's scalar fields indicating energies, like an energy landscape or energies in different areas of a coordinate system, pressure fields, distances from objects, vector fields, and matrix and tensor fields more generally, such as strain fields. So there's a lot of ways that we use coordinate systems. And now the next part of this statement, which I hope will also not be controversial, but I'd love to hear other people's opinions, is that coordinate systems are fundamentally arbitrary. So in physics does not use coordinate systems intrinsically to operate. We use coordinate system to write down physical equations, but there's no little coordinate systems like running around as fundamental particles in physics. And so we choose a coordinate system, but our answer for what happens next should not be biased by that choice of coordinate system. We may find certain coordinate systems more convenient, but in the end, how we're modeling the world should not depend on them or their particular form. So let's take, for example, the teddy bear and robot system again. So they're in 3D space. I could use many different coordinate systems to describe this system. But suppose I just have these two coordinate systems, 1 and 2. And if I were to articulate locations and orientations using these different coordinate systems numerically, these descriptions look drastically different. And the challenge is that if we would like to use machine learning to model physical systems, but it doesn't really know about this symmetry of coordinate systems, that we're always free to translate, rotate, or even invert from a right-handed to a left-handed coordinate system. We usually choose right, but that's just a convention. We have always this freedom to change our coordinate system, but traditional machine learning will not know about any of those relations. It would have to learn it. And there's no guarantee that it really gets the idea. So this could be problematic, or it's something that you just have to brute force teach it to do, which maybe means you're spending a lot of parameters on teaching it rotations instead of, in my business, teaching it quantum mechanics, which I'd much rather it spend its parameters on learning quantum mechanics. So the question is, can we use coordinates with machine learning without being biased or thrown off by them? So can we use it just as a tool and not be biased by that tool? And so Euclidean neural networks, and I'll say Euclidean neural networks, but in this talk, I'm specifically talking about the implementation of them for 3D space, have this property where it sees the descriptions for 1 and 2, and it understands that it's the same thing, just described differently. And that's even without training. So it does not need to learn this. This is a built-in property into the very operations of these networks. Any questions on this so far? Okay, let's talk about maybe some properties. So to get a little bit more formal with what some of the properties that these networks have is we often draw these diagrams where we say, if my neural network is the function f, and I have some input, in this case, I'm giving maybe the coordinates and atom types of a molecule, and I want to predict the forces, these little vectors, I can go ahead and make that prediction to the forces. I could also, instead, rotate my molecule, put it through the same function, and I am guaranteed that the forces will be the same, just rotated appropriately. So I can either rotate the inputs or rotate the outputs, and I'm guaranteed to get the same answer. And this property is called equivariance. And the specific notation for those that are curious, these d of x and d of y are articulating how does our group, in this case the Euclidean group of rotations, translation, and inversion, how does that act on the vector space of the inputs X, or the outputs Y. And they may not look the same. It's still the same group, but how it's represented in that vector space may look different. Especially, if you're looking at vectors versus a tensor field, it's going to look different how those rotate. The other thing I want to emphasize is that in many of the applications I work on, I focus a lot on point clouds because atoms are point-like and it's a useful Oh, okay. So none of it was recorded. Okay, no worries. All right. So we will also have generative models. So being able to generate molecules, in this case, one atom at a time, using a model we call symphony, where we're going to use spherical harmonics to articulate distributions of putting atoms around other atoms. We'll also talk about hierarchical representations of proteins. And if we learn hierarchical representations using these types of networks, what are some of the patterns that we see in the representations it learns in the middle of the layer? And then last but not least, I want to give an example for extracting or detecting anisotropy in little eddies in fluid dynamics, basically confirming what's called the Kolmogorov hypothesis. So those are the applications that we'll come back to. One moment. It feels like it's working.
It does, yeah.
Is it just, or, I mean, it makes sounds.
Maybe it was where it was positioned.
It's the angle?
Yeah, maybe.
Maybe, yeah. Okay, but I'm happy to use this. Okay, cool. Thank you. All right. So before we get our dessert, we will eat our vegetables. And I'm going to tell you about what makes these networks a bit different from your just run-of-the-mill neural network. And it's really three main ways. This is not the order in which we figured this out. We actually started from geometry and then realized that we needed special data types. But first, we'll talk about how we encode data to these neural networks. And we do this actually using a branch of mathematics called group representation theory. So if you've ever heard of the term irreducible representations, they're coming up. So get excited. If you haven't heard of irreps, don't worry, it's going to be okay. Then there's how we interact these data types. We don't just do multiplication. Our multiplication now has certain rules attached to it in order to preserve symmetry. And then last but not least, we also have constraints on how we parameterize functions of geometry. And so we'll go through that last. Any questions before we dive in? So let's start with data. So let's say you hand me a data set and you tell me that it predictably changes when I apply 3D rotation and inversion. We're gonna mod out translation for now because that's usually handled in a different way. But you tell me, you give me this data set and you say, if I rotate and invert my coordinate system, I know how this data set transforms. I tell you that, okay, that means that I can provably break up your data into more fundamental data types. I can decompose it into, you can kind of think of it as an orthogonal basis. So any type of data that's acted on by the group of rotations and inversion in 3D, so O3, can be broken up into simpler components that are indexed by two numbers, L, which you can kind of think of as an angular frequency. If I rotate my coordinate system, how quickly does this feature change? If L equals 0, it doesn't change. It's invariant under rotation. If L equals 1, it changes as the same rate as I change my coordinate system. Something like a vector is an L equals 1. Something like L equals 2 would be something that's similar to parts of a 3x3 matrix. So it may have double the frequency. It's twice as affected. The other one is parity. So this comes up when you think of chirality and things like this, but even not in those special cases, it's just defined as even or odd, and it is whether or not, if I invert my coordinate system, so left to right, or if there's a mirror, does it incur a minus sign? If it doesn't incur a minus sign, it's even. If it does incur a minus sign, it is odd. So let's go through a couple examples. So let's just do L equals 0 and L equals 1. So L equals 0, angular frequency 0, does not change under rotation. Something that's an even parity L equals 0 feature is called a scalar. Something like classification labels. So if I have an image and I detect a rabbit, if I invert that rabbit or rotate that rabbit, it's still a rabbit, hopefully, unless you've done something terribly wrong to the rabbit. So that is a scalar quantity. But what about a pseudo scalar, which is odd parity? One great example is if I was classifying right hands. So if I were to invert my image or mirror it, that right hand is going to turn into a left hand. They're still related. And actually with these types of networks, I only need to train on right hands to be able to identify left hands. So you automatically kind of get the recognition of this pattern. We're doing okay? We're going to switch it back. Okay. Okay. Yeah, please. Thank you. All right, so oh, yes, question. Yes. Yes, so specifically that it predictably transforms, or yeah, basically that I can apply group action is more the kind of technical way of saying it. But if there is a way to act on that vector space with that group and it changes predictably, I can provably decompose it into these fundamental data types. Yeah. Okay, so let's do L equals 1. I love doing L equals 1 because it turns out that you know pseudo-vectors very well. Okay, so odd parity, L equals 1 are just vectors, coordinates, forces, things that we're kind of used to. Pseudo-vectors are rotation axes. And one of my favorite ways to explain rotation axes is cross products. So the way I generate a cross product typically is I have a vector. So I have vector 1, vector 2. So let's say x, y. I take the cross product and I get z. Okay, now I need to show you that this thing doesn't change under parity. So now we're going to take the cross product of minus x minus y. So if I take the cross product of minus x minus y, I still get z. So if I cross product two vectors, I get a pseudo-vector. And so hopefully that gives some intuition that this is a very similar object. It's still vector-like, but its properties under inversion are distinct. And so it's a distinct data type. Questions on that one? All right. So to kind of explain why do we do this to ourselves, these distinct L, so angular frequency and parity objects, are called irreducible representations, or more affectionately, irreps. And these are distinct vector spaces that basically stay in their lane under rotation and inversion. So if I hand you a pseudovector and I apply a random rotation to it, it's still a pseudovector. If I have a vector and I do the same, it stays a vector. So what I'm showing here, this GIF is just showing random elements of rotations and inversion applied to this vector space of a scalar, a pseudoscalar, a vector, and a pseudovector. And the important thing is that you notice this matrix is block diagonal. And so these vector spaces are not talking to each other. They are independent. And so this is sort of why we use this basis. Is it actually makes it much easier to preserve symmetry because we know how these different chunks behave and which pieces talk to each other or not. So there are many types of Euclidean neural networks, or it's a large class, it's a zoo of models. So there's many models that have symmetry built into it that may only use scalars or vectors. And this technically limits the expressivity of the model. That might be fine. The models might do very well on their tasks, but it's important just to know, just to have in your toolkit, that there are other options. There's other data types that you can also act on. So we'll talk a little bit about computational efficiency of why you may not want to use all the data types, but we'll come back to that later. Okay, let's talk about interacting data. So I'm going to stick with scalars and vectors just as a motivating example of where these other data types come in. So you might be saying, well, I only deal with scalars and vectors, so these other data types, maybe I can get away without them. And that still may be true, but I'd at least like to motivate where these other data types may come from, even if you're starting from humble scalars and vectors. So what are all the different ways we can interact scalars and vectors? I can take a scalar times a scalar, gives me back a scalar. Easy. If I have a vector and a scalar, the scalar scales the vector, hence why we call it a scalar. So I can't change the direction if I'm interacting with a scalar. If I take two vectors, the most general operation is the outer product. So it produces a 3x3 matrix. It's not a scalar, it's not a vector, and it also does not have a single angular frequency. It's actually composed of multiple irreps, which we have here. And you may also wonder, well, that's not the only way I could interact vectors. I could have also done dot products and cross products. Those are actually contained within the outer product. So if I look at the trace of a matrix, this is equivalent to the dot product of two vectors. This is an invariant, and in this case, it's also even. Then I have the cross product, which, as we discussed, is a pseudo vector. So it has parity is even, and that is your cross product component. And then last but not least, the thing that's left over is your symmetric traceless part of your matrix. Importantly, you have 9 degrees of freedom on that side of the equation, and you have 9 degrees of freedom on this side of the equation. We're preserving dimension. We're just breaking up those dimensions, kind of using a different coordinate system. So it's a different basis question. Oh, sorry, when you say most, the most general operation. They are bilinear, yes. I think that's an appropriate way to put it. I guess I think I even mean it just in the sense that I can't think of another operation that I can do to 2 vectors that's symmetry preserving. Like, yeah, there's, as far as I know, I think the proper way to say it is if I have 2 vectors, this is all I can do. Like, this is the maximum number of types of distinct symmetry allowed operations. Yeah. So, but you're totally right. This ends up being a bilinear operation. So the point I want to make here is that even if you start with scalars and vectors, you end up with pseudovectors and L equals 2 even objects, even just by performing a single operation. Now, you can choose to restrict yourself to scalars and vectors, but you are going to throw out these types of interactions. So they will not exist in your model. And another way of saying that is if you only use scalar and vectors, these are the only types of operations you can use that still preserve symmetry. So scalar, scalar, vector, scalar, and dot products. So, and that may be more than sufficient for what you're doing. Again, I just want to emphasize that there are more options for you should you need that expressivity. Okay, so let's talk about this operation is more generally called a tensor product, and specifically a tensor product decomposition. Now, a naive tensor product, as we said, preserves dimensionality. So it preserves all the different ways that we could have interacted the data. So if I have a vector space that's size n and a vector space that's size m, I have an n times m dimensional vector space. This becomes quickly computationally inconvenient to store on my GPU. So it preserves dimension in the most naive sense. So in order to practically scale these models, we need to do some pruning. So then the question is, how do we prune these interactions in a way that preserves symmetry? And this is yet another reason why we use these IREP basis, because we can essentially prune these interactions by dropping entire IREPs. So I can choose, okay, I'm going to not include this pseudo-vector term, but I have to drop the entire pseudo-vector term. I can't just drop some dimensions of it, because eventually I'm going to rotate, and I'm going to rotate out of those numbers in the basis and into the ones that I'm missing. And so one of the reasons, again, that we use this IREP basis is because it makes it much easier to choose which interactions we keep and which ones we throw away for computational efficiency. So we decompose, for example, our outer product, prune these interactions. For example, we could choose to leave off the L equals 2 interaction. And in practice, this is what we build an entire Python library called E3NN that does this under the hood, so that hopefully you don't have to spend too much time figuring out how to do this. Say that one more time for me. Yeah, okay. So the question, I guess I'll repeat it. I don't know, is the room mic'd? I actually don't know. I'll just repeat the question. So the question is, like, do you lose expressivity if you decide to drop this? And I think in most, like, mathematically precisely, yes. In a practical sense, it can depend on your application. So in some cases, we find that matters. In some cases, less so. So it can be data set dependent. Yes.
Do we know if when I use a subset of the IREPs, do I span the tensor product space densely or some such thing?
I see.
So is there a reason why practically you don't lose much?
Okay, so yeah, so is there practically is there a reason why we don't lose much? I think part of it could be you can either build that stuff up later, or sometimes there's a lot of different ways to play with like what else you're using. Because neural networks are typically compositional, meaning I will take the same layer and then repeat it many different times. You may have many different opportunities to get similar information, particularly as, like, let's say I keep up to L equals 1 and I keep the pseudo vectors. That information can then maybe interact with some of the similar information later down the line, but produce lower order objects. So that's not a very simple answer. But I would say at a high level, yes, just because you may have many opportunities to interact with the same data in a neural network. But we don't have like a formal understanding of why this is the case. People have put out some very interesting empirical results where you may even use certain irreps during training, and then when you actually run them, like once you've converged, some of those irreps may no longer be important. So. And there's like a bias towards lower order irreps as well, because you can kind of think of it like a Taylor series. These higher order terms are kind of like an expansion. Okay, yeah. There is sort of like that kind of expansion bias. Yeah. Yeah, certainly when you just look at like the raw tensor product, I think that intuition works well. I think once you start adding an activation function, some of that intuition breaks down a little bit, because you're no longer like, you're still dealing with like properties of the vector space that are linear, but the function itself is not linear. It's not like we're applying like just a Hamiltonian or something. So one might say tensor products and irreps seem complicated. Is there another way? Can I just get rid of my coordinate systems altogether? And this is another valid avenue to go down, which is to just describe your system using invariants. So things that don't depend on your choice of coordinate system, like pairwise distances or angles between objects. So folks have also investigated this avenue, and that can be very effective for certain data sets. And then equivariance, we're going to keep the coordinate system around, and outputs change appropriately when we change the inputs with a coordinate system. One thing that has been observed across multiple data sets, at least in the atomistic sciences, those are the examples I'm aware of, is that equivariant methods are more data efficient than invariant methods. And what I mean by that is essentially the log of the error of the model on the validation set versus the log of the number of training examples has a power law, but the power law has a more favorable exponent for equivariant methods. So it has a much more steep learning benefit from adding more data. And now this is a schematic, but there's actual plots in these references if you would like numerical values. These slopes can be architecture and task dependent. So like exactly how much of a gain will be dependent, but we tend to see a pretty reliable from when you have invariance to when you turn on at least some amount of equivariance, there's a fairly noticeable dip. Is there a question? Yes.
There are some tasks which are per nature equivariant.
Yes.
And more general question, down documentation in the training examples, or is that like the mother focus?
Yeah, so I'll answer in reverse order. So this is just comparing invariant to equivariant models. It's not non-equivariant models, which is actually sometimes a very difficult comparison to make. In the limit of enough training and contrastive learning and augmentation, you can use a non-equivariant, and enough data, you can use a non-equivariant model to achieve similar accuracies. It's a little unclear about robustness, smoothness, generalization, that kind of stuff. I think that's the part where we have to be careful to measure. But this is just comparing like, if you turn on, like if you have scalars or you turn on vectors. And then your other question was, what about things that are inherently invariant? Does it matter like image classification or predicting energies? And we noticed that even if your output is an invariant quantity, having equivariance in between is helpful. one way you can think about, even if you at some point in the network switch to invariants, and you can kind of think of it, it's giving it a little bit more time to do feature learning and crafting things that would be good invariants to use for the rest of the network. Question. That's true. It's a strict subset. Yes, exactly. Yeah. So scalars are L equals 0 even parity. Pseudoscalars are still considered equivariant because they have this sensitivity to mirrors. The other thing that we've noticed is that for many tasks, particularly those in the atomistic sciences, so for forces of quantum mechanical systems, we additionally, and especially things involving transition metals, so things in the middle of the periodic table, higher order interactions also continues to improve data efficiency and accuracy. So we'll actually see additional, it's not as drastic as the jump from L equals 0 to L equals 1, but for L equals 2 and L equals 3, we will continue to see some steepness. And again, the references are in these slides. But it's not just our group, but it's like many other groups are also observing this trend. Now, of course, your mileage may vary depending on your data sets. So you'll have to balance computational efficiency and expressivity. Okay, last but not least, let's talk about featurizing geometry and more concretely, how do we actually represent our system to these models? So typically the input to an E3 and N is going to be geometry, so where things are in space, and then what's living at that point in geometry. So this is for a point set, but you could imagine something analogous for images or meshes. So let's say I have this 2-point mass system, and these point masses have a mass, and they have an acceleration and a velocity vector. So I have the geometry, their coordinates, and these features that are kind of stacked. So each row belongs to one of these points. So I'm not done yet. I also have to tell the model what are these features that I gave it? How do they transform under rotation and parity? So I have to tell it, well, the first thing's a scalar, the second thing's a vector, and the next thing's a vector. In order to preserve symmetry, you first have to tell me what you gave me. So there is this specification of what your inputs are. So what do we do with the geometry? Because now we have like these two features. What do we do with this? And what we do is we typically use convolutions or some kind of function inspired by convolution to interact what's living on the points in space and interacting with the geometry itself. And specifically, our filters, our convolutional filters, which rather than being defined on like a specific gridded domain, we can choose to define it over a continuous domain. So rather than like a fixed W matrix, we have a continuous function of relative distances between, in this case, points. Our function for our filter is also constrained in order to preserve symmetry. We have a learnable radial part, so we are free to learn whatever function we want for the radial component of the filter. And then the angular part of the filter is built from spherical harmonics. And the reason why these spherical harmonics is that they actually transform in the same way as these irreps. So these spherical harmonics are called the basis functions of 3D rotations. So they actually transform as L equals 0, spherical harmonics transform as scalars. L equals 1, spherical harmonics transform as vectors. L equals 2 is 2e, L equals 3 is 3o. So they have distinct parity and distinct L. So if I rotate these functions, they stay in their lane. If I rotate an L equals 3 spherical harmonic, like I have a bunch of coefficients, in this case I'd have, L equals 3, I'd have 7. So I have my 7 coefficients. I apply a rotation. I get a new set of coefficients, but they're still all L equals 3. So this lines up well, and now we know how to interact them and everything like that. Please. Yes. It would be a different family of functions. So if you're in if you're doing O4, then you would have your hyperspherical harmonic functions. So you do have to figure out kind of like what are your harmonic polynomials for that system. But for 3D space, we're very familiar with these. But yeah, certainly for arbitrary groups and arbitrary dimensions, like constructing and even representing your functions could be non-trivial. Not live. I could comment on it offline because I definitely had like a notebook where I was playing with some of this of like, okay, how do I do this for like SO5 and things like that. There are some really like concise analytical formulas for the dimensionality of these functions. Also, you'll start gaining additional indices depending on your group. So I believe even SO4 has 2 indices that you carry, like 2 L's in a way. Yeah. Okay. So looking at the time, do I have 7 more minutes? 3 or? Well, more. I have more. Okay, great. Then I won't rush it. Let me know when I'm approaching time. All right, so let's go back to applications. Now that we have had our vegetables, we can now have our dessert. And so let's talk about different models and how we've actually used these. So let's start with regression. So first, a little bit of background, since I suspect that many folks in the audience don't do molecular dynamics. So probably the first successful use case of these Euclidean neural networks was for learning interatomic potential. So given a configuration of atoms, what are the forces experienced by the atoms? Specifically training on very expensive, computationally expensive quantum mechanical calculations that typically take hours to days to weeks on supercomputers. So this would be something like density functional theory if you're familiar with that. So essentially we have a configuration, and what we train the neural network to do is to predict an energy. And then because we have this network in an auto differentiation framework, we can define a conservative force field using derivatives of the energy with respect to those input positions and get out forces. This is one way to do it. With more modern networks, sometimes people will just directly go to forces because the risk of having something non-conservative is low enough, and the computational cost of doing this back prop is too expensive. So there's like a bit of a trade-off, but I think it's just like a nice thing about auto differentiation frameworks is that you can do these types of derivations within the framework. So whether we go directly to forces or through this derivative step, we can go from structure to forces. And there is a whole zoo of different equivariant models that people use for this. So there's an Equip and Allegro, which is coming out of Boris Kaczynski's group at Harvard. I was involved on Equip for early days. We have MACE coming out of groups like Gabor Chani and friends. We also have TorchMDNet, and there's many others, but these are all equivariant interatomic potentials. And the specifics of what types of tensor products they use, or even these like additional tensor products of features, which is called body order interactions, all vary. So a whole zoo there. One of the things that's really exciting about this is that while quantum mechanical calculations at the level of density functional theory can really only be applied to systems of size 100, maybe 10,000 if you work with specific assumptions, it's still limited. There's 10 to the 23 atoms in a mole of something. So if we can only do 10,000, that's a bit limiting. So what's really exciting, and this again is Boris Kaczynski's group, Allegro, which is a very well-scaling model, was actually a finalist for the Gordon Bell Prize, which is like the Nobel Prize of supercomputing. So it was a finalist for scaling Allegro to bring quantum mechanically accurate predictions to something the size of like an HIV capsid, which is about 44 million atoms. And this is something that you just can't do with the traditional method. So it's not even just accelerating the method, which, I mean, we're accelerating the methods by 10 to the 6. So that's a significant order of magnitude, but you're also just able to attempt these calculations on something that's just much bigger. Now, how do you validate it? That is the big challenge. So hopefully experimentally, because in the end, we really want to predict things that are real. But validation is a whole nother realm of like, what do you do once you scale these calculations? But it's at least exciting that we can now attempt these calculations versus before we just could not. So within my own group and also with collaborators at Meta, so we made a equivariant transformer. So you may have heard about transformer architectures. They're all the rage for natural language processing and even image generation. the way I like to think about transformers is that they're actually quite similar to convolutional neural networks in the sense that you care about the relationship in space, like the positional relationship between two objects. But additionally, you have an attention mechanism, which is that your kind of filter cares about what it's looking at. It cares about where am I looking from and what am I looking to. So it's like a convolution that depends not only on your position, but also the features that are living at those different positions. So we made an equivariant graph transformer that we call Equiformer, and we trained it on many different types of atomistic data sets. And one thing that we just wanted to see is if we actually go ahead and build a big model, so something that has tens of millions of parameters, how well does this model perform on complex atomistic data sets? And what we find currently is that Equiformer V2 so far has topped the leaderboard on any data set that we've thrown at it. And this is, trained by my group, but also largely trained by Meta. So there are these catalytic data sets. So the Open Catalysis project for, they have like alloys and they have oxides and you have molecules that come in. And what you want to do is you want to predict energies, forces, and also relaxed structures. So maybe I give you an initial structure, but it's not energetically happy. So we relax the structure. So these are the types of tasks involved. And so we're currently topping the leaderboards for that, as well as the open direct air capture. There's these very porous materials called MOFs, or metal organic frameworks. And so we're topping that as well. And then more recently, Meta recently announced the open materials data set, which is a bunch of inorganic materials. I see your question. I'll finish my sentence and then I'll get to you. And also there's like the materials project trajectory data set. So I know I'm throwing a lot of different data sets at you, but I'm really just trying to emphasize that you can take things from other branches of machine learning and make equivariant versions of them. And if you do that faithfully and you scale the models, you can still get those big gains that you see just from general scaling of models. So that was the main point for like berating you with a bunch of atomistic data sets question. That's one part of it, yeah. Yes, this specific architecture, how it works. Yeah, so there's many things going on. So we still have these like spherical harmonic filters. Equiformer V2 actually uses a tensor product operation, like a modification of the tensor product that's still equivariant, but it makes it a lot easier to, it's a lot, I want to say computationally less expensive on current hardware and current compilers for doing these convolutions. It's from equivariant spherical channel networks from Meta. So there's like another little specific type of tensor product in there. There's also different types of normalization layers because this model is able to go to like L equals 8. And so it turns out that how you normalize different types of irreps is important because you can't make assumptions of like the dimensions being completely uncorrelated. So you need to take that to account for your normalization. And then the attention mechanism is probably the biggest difference between Equiformer and other models is that the attention mechanism is really using tensor products, not just a dot product, but there's actually like multiple tensor product operations involved in the attention mechanism. So it's a very equivariant operation, I would say. Does that answer your question somewhat? Many pieces, yeah. Correct, yeah. So there's many different components that make Equiformer work, not just like one little piece. So it's really the normalization, the attention mechanism. I would say those are the biggest things. The normalization and the attention mechanism are kind of the big innovations for Equiformer, and also making use of Meta's spherical channel network operation in order to scale to higher representations was very important because we even see accuracy gains on these data sets going up to L equals 8. I think L equals 6 was like the sweet spot, but I think even L equals 8, you still see some improvement. So this was sort of like my more traditional ML slide. Look, we're topping the benchmarks, which I'm still very proud of, but I also want to talk maybe more about some kind of maybe cutesy science problems. So let's go on to generative models. So the first model that I'd like to show is symphony. And I'm showing this big graphic here, but I'm going to break it down in the next slide. So symphony is what's called an autoregressive model. So it builds atoms up one atom at a time. Okay, so first of all, let me back up a little bit. What makes generating molecules challenging? Well, molecules are discrete and they're variable number. So having a generative model that can basically generate a variable number of things is non-trivial. Now, diffusion models can do this basically by initializing more atoms than you need and then having the atoms sort of die off. But this is a different type of model where we're actually deciding on the fly how many atoms we want. So it's a bit of a different modality. So let me kind of break this up. So symphony generates molecules one atom at a time. So I'll just add different atoms. But between the predictions, we actually split up the prediction into multiple pieces. So given a molecular fragment, I'm going to condition on this fragment saying, here's what I've got so far. Which atoms need a new neighbor? And so the atoms discuss in the network. And then they come up with a focus atom. So which atom is going to gain a new neighbor? So this is just a probability prediction. And then we ask, what type of atom does this atom want as a neighbor? So in this case, we choose hydrogen. And then the key thing of what Symphony does is how it does this prediction of the different positions for this model. So we want to predict distributions of possible positions, which we're going to use spherical harmonics for. And then from that distribution, we sample where we put the atom, and then we feed that output back into the model. And this is what makes it autoregressive. Now, notably, the sampling is stochastic. So there's many different ways that you could build up that molecule. Or even if I start off with, like, for example, the first 4 steps, I may generate a different molecule. So maybe instead of choosing hydrogen, I chose another carbon. Like there's many molecules that have that similar subgraph, but I might build other types of molecules from it. So you're kind of representing the distribution and kind of sampling as you go. But notably, when you sample, you are actually breaking symmetry. However, in aggregation, if you actually run the model multiple times, it is a symmetry-preserving model. So for example, if I was generating a methane molecule, so that's CH4 over there, and I start from this fragment of 1 carbon atom and 2 hydrogens, and I'm going to add another atom, well, I could add the one to the left or the one to the right, and then add the remaining atom. And so with this model, you're guaranteed to get both of those paths with equal probability. So even if you are using a symmetry-preserving model, you can still have sampling procedures that are locally breaking symmetry, even if the model itself has learned a symmetry-preserving representation. So just zooming a little bit more on this particular graphic, I want to highlight this area here. So this is the part where we predict the positions. So spherical harmonics can also be thought of a basis for representing signals on the sphere, or it is a basis for representing signals on the sphere. So what we've done is we've parameterized this distribution over space into radial and angular functions. But we don't just use the spherical harmonics or radial functions. We additionally want them to be more confident in their prediction. We want them to be more peaked. So there's actually an additional step where we push it through an activation function like softmax. And this actually makes our distributions much more peaked than they would be if we're only using a finite basis of spherical harmonics. And so that's kind of a neat trick. You can actually get very peaked distributions even if you use a relatively low irrep order. Yeah, so we actually do sample the radial and the angular parts separately. You don't necessarily have to, but we typically choose the radial and then the angular. So we're basically like, we keep tracing out aspects of the probability distribution as we kind of go through this process in the middle here. But you could do it in many different ways. So it's really just a convenience or implementation detail question.
Do you think that there is a benefit of autoregressive where you add an atom time instead of
Diffusion. Yeah.
yeah,
Yeah. So comparing autoregressive and diffusion. So to be clear, these models do well on atomistic benchmarks, but diffusion models do better. So diffusion models are very accurate. I am personally excited about things like Symphony for hierarchical generation, because even though Symphony itself only does you only have one focus and one atom at a time, the eventual motivation for this work was, let's first do autoregressive one atom at a time, and then let's scale it to where we can lay down entire motifs at a time so that we can technically get exponential scaling of the number of atoms. So that's where I see Symphony being useful. So diffusion models, you typically have a fixed token length, or a fixed number of atoms. But if you want to kind of encode and decode hierarchical structures, I think this may be an interesting approach. So I think it's complementary, and I also think it can depend on what you want to do. So I was actually talking with Ian Abrams over at Yale, and he was very excited about this for he's like, oh wait, you could actually build joints for robots using this or something. So I thought that was kind of a cool way of thinking about it. So I think it's just a different approach. I'm not going to say whether it's better or worse. I think accuracy why it is not as good because we don't adjust the positions once they're laid down. Could you hybridize the model so that you have a hybrid diffusion and Symphony model? I think that would be interesting. We have to make sure it actually trains. So that's kind of an open question. Yes, yeah. So that's another thing too, is that the way that we've broken this down is that you can actually kind of intervene with the generation process in various ways. I do think that this method of generation may be more amenable to design or human interference with the design process. So there's more handles to it, which again, it depends on your use case. You can also condition various things for diffusion models too. But this one, it makes it very clear when you can intervene. I could just force it to put a carbon down, even if it doesn't think that's very likely. Yeah, so your conditioning process would still be built from an equivariant model. And there are some subtleties actually for how do you sample higher order tensors. So for spherical harmonics, it's clear how you do it, but for other ones, maybe not so much. Are you sure I'm not over time? Now I'm over time. Okay, I was wondering. Okay, so I'll be somewhat quick. So a fucus this is a model that auto-encodes proteins. The important thing here is what we're doing is that we're using the backbone of the protein. We're coarsening the backbone until we get a single atom. So we're trading out geometric degrees of freedom for featured degrees of freedom. And this is interesting for multiple reasons. You could apply a diffusion model on this internal representation right here. So on the Z, so rather than generating all atom representation, I can just generate a point that has rich tensor features. So that's an alternative way of doing generation. But what we found was really interesting that we didn't expect is that this model seems to encode physical deformations of proteins, which is very challenging to do. So let's say I have a protein, like an enzyme that opens and closes. If I were to just interpolate the 3D coordinates, it would be a mess. Nothing physical, clashing everything, don't do it. It's usually a complex deformation. But if I do that interpolation in this learned space, we get physical deformations. And we didn't train it to do that. We didn't show it intermediate points, we just showed it endpoints. So something about the bias in the model or some aspects of our training procedure encouraged this type of latent space, which is useful. So that was kind of an interesting thing. And this is with my collaborator, Joe Jacobson in the media lab. Last but not least, I won't go through the full of this, but essentially, if you preserve symmetry, that means the outputs of your model have to have equal or higher symmetry than your inputs. So I put in a tetrahedron or an octahedron. Anything that comes out, like these spherical harmonic signals, are going to have the same symmetry. And what this means is that if you want to have an output with lower symmetry, you need to give the model more information, or you need to have a sampling procedure. So this is actually work with Robin at Northeastern as well. So we have two different works but essentially finding ways to uncover asymmetry in models, and also, and the second work is with my grad student Yu Qing for handling spontaneous symmetry breaking. So if I have a square and I want to deform to this rectangle, a equivariant model will predict two averaged rectangles, which is actually a feature, not a bug. And what it's saying is that, well, which rectangle did you want? There's two of them that are symmetrically equivalent. And so in these two papers, we figure out two different ways of handling this. And I won't go through it. Well, you're free to ask questions about it. What I do want to say is that in the case where we can learn asymmetry, what we did is we used relaxed convolution. So these are equivariant models that can learn symmetry breaking parameters from the data. And what we were able to do is take a fluid dynamics image. We broke it up into sort of, we did different scale separation of patterns. So you take the Fourier transform, you kind of do some bandwidth limiting, you project back into real space. So now we have different images with different patterns. And then what we did is that we learned asymmetry at different length scales. And what we observed is we looked at the magnitude of symmetry breaking as a function of length scale. So smaller scale features are going to be have a higher wave number. And what we see is that most of the symmetry breaking is happening on large length scales. And this is what you would get from the Kolmogorov hypothesis, which is small turbulence vortices become isotropic, even if the large scale ones have broken directional symmetry. All right, so I'm going to put up my takeaways, and I'm very happy to answer any questions. And thank you guys already for the great questions. Yeah, especially the online folks.
It was such a clear presentation of these ideas. It was really great. You spoke a lot about kind of like the function class and how it should be designed to incorporate the kinds of invariances the data has, and the equivariance the data has. But have you or others studied in detail what this does to the learning dynamics of a neural net? And is it always a good idea to do this? Does it sometimes cause problems? Also, even for standard neural networks, there's always the issue that we're kind of iterating by kind of mostly empirically. The community of practitioners is coming up with tricks that help with training.
Yes.
And so where are we on that curve in classes of networks like these that are perhaps studied by smaller sets of people?
Great question. So yes, the same types of things of like figuring out training tricks, normalization layers, these sorts of things apply just as much to us. Even though, we say, oh, we're more principled. It's like, yeah, but we're still optimizing this very weird physical system. So yeah, we're certainly susceptible to training tricks. There is evidence that that adding these constraints can make optimization more difficult, but it is difficult and unknown exactly like how to quantify that, besides people just saying, oh, well, we made a non-equivariant model that also fits the data to this level of accuracy. So I think as a community, we have to figure out more ways to benchmark models, not just in terms of the raw accuracy, but things like smoothness of the representation space, other things that we care about that are domain specific. I have, so Yu Qing, who was involved with some of the symmetry breaking work, he's actually looking specifically at this. And we're also trying to interpolate between like a non-equivariant and invariant, or sorry, a non-equivariant and an equivariant model. That's something that Alyssa, also part of the symmetry breaking, and with Robin, that we're trying to figure out. So I would say this is an active research question of like, what are good ways to answer that question? Because it's coming up a lot more. So yeah, to be determined, but there's definitely a lot of room if this is of interest.
Hi, this is wonderful.
Thank you.
I am thrilled by your presentation and challenged, actually. Could you please tell the students, what did you study?
Sure.
Obviously, you studied many things.
Yes.
But can you please tell them what made a big difference in your professional life?
Absolutely.
It's clearly suggests a much more integral education than what we do today.
Sure, yeah.
And many students get that they just have to find, something about AI. So please tell them.
Sure. So maybe I'll give maybe to build on the wonderful introduction from Kostas. So in undergrad, I did study physics, but I also for a while was a double major in architecture. So ultimately, architecture, yes. So I got a minor in architecture, and that actually influenced a lot of how I think about geometry and how I think about hierarchy and geometric motifs. I was originally in particle physics. So I worked on the Large Hadron Collider when they discovered the Higgs. I worked at Fermilab on neutrino physics. And that really got me interested. Chemistry came later, actually. So particle physics really taught me about large collaborations and the importance of working with folks that had very different expertise to move towards a common goal, and the importance of being able to speak a common language. The last studio that I took in architecture was on self-assembly and that notion abstractly for generating geometry. And that's actually where I came to learn about materials. And I was fascinated by the fact that copper could have the same type of local structure, but actually had all these polymorphs. So this is the diversity of geometry that you can find in the atomistic systems. And so I wanted to switch over to materials physics in grad school. And I started off by wanting to make things, to make materials. So yeah. And then eventually I realized I just really liked computers. So I went back to the theory side of atomistic systems and then got frustrated that neural networks couldn't handle 3D geometry. So worked on that problem. So yeah.
Hey, I also have a general question about the equivariant network.
Sure.
So actually, I observed there are some recent works that they always have a local equivariant frame, and then they just predict the property in this local frame and then go back to this frame, and then actually the higher order features are just the polynomials with different bases of the axis. So do you think there's any drawback of this work comparing with the network with the higher order tensor? And also have another related question is tensor. We don't have
It's a great question.
We don't have equivalent large model, but actually the large model are really prevalent. So is there any similar way that we has a equivalent architecture as the bottom to localize it, to canonicalize it, to have a equivalent frame and canonicalize it, then make use of the large model or the other non-equivalent conventional network? What do you think this trend and compare with the traditional equivalent network, does it have any potential drawback or advantage?
Great. Okay. So high level answer to your question. So for folks that use local frames and typically going to an invariant, I think that's a perfectly fine thing to do. I have no qualms with it. And there's for folks that do frame averaging, there actually are connections. In the limit of infinite frames, you're basically there are some really beautiful connections. So I have no problem with frame averaging. It does make it more difficult to have intermediate higher order representations. So that's the only thing that concerns me about it. But if it works for someone's application, I think that's fantastic. The second thing that you're talking about, which is essentially, we have these large models, we have equivariant models, can we kind of connect them? So the process of tokenization that is used in large language models, you could use, for example, equivariant models to develop rich tokens. So this is actually something that we have not formally an undergrad, now a master's student kind of looking at specifically for local environments of atomistic systems. So I think there's a lot of interesting opportunities to interplay between these different types of models. Language models are fantastic because they provide an interface. Language models are great because we are used to using language to articulate our ideas and thoughts, and that's not going to change. So I think connecting different types of models up to language models, I think, is really interesting. Having the language model directly predict things like forces and energies, I'm skeptical of, because that's going to be so dependent on the type of data it was exposed to and how it was exposed to that data and how it was done, how masking was done. But I certainly think combining these different models is definitely possible.
Thank you.
So it's a fantastic talk. The way you've used all the symmetry is primarily for computer vision or for the molecular upscaling, that it's a supervised learning process. But from physics, all these symmetries would be like the jumping off point. And so,
Or I would even say I don't even include the symmetries that we typically discuss in physics.
right, yeah, so
Yeah.
in terms of like Noether's theorem.
Yeah, we haven't touched, yeah.
Can you comment on what you view as the potential future applications, people doing that?
Yeah. So just maybe some context. So here we have imbued models with the symmetry of the embedding space. So this is just using the fact that the physics in your particular domain may play out in what looks like three-dimensional space. But in physics, when we talk about symmetries, we're typically talking about conservation laws, when that requires introducing the notion of a Lagrangian. So essentially, if we have this Lagrangian, this description of like kind of how the dynamics of our system evolve, and we have continuous symmetries of derivatives of the Lagrangian, and that's Noether's theorem. That's what gives us conservation of energy because of the invariance of physics with respect to time. It's what gives us the conservation of momentum because the invariance of physics with respect to space, and angular momentum for the invariance under rotations. So it's a much bigger assumption. So we don't build any sort of Lagrangians into our models. There are other works that have done this, and I think they've been effective in a variety of regimes. But I certainly don't do this because doing this for many body molecular systems is very painful. So, it's a linear system, and yet we really struggle with quantum mechanical systems. So my group doesn't tend to work on that. But I think depending on the types of problems you're looking at, especially for like classical dynamics or fluids and things, or these types of like evolving PDEs, ODEs, I think people have had a lot of success with kind of baking more in Lagrangians, but I don't have much to comment on it besides that. One more comment is that, so I have two very fluffy rabbits, and one of them is named Emmy Noether, like on her pedigree. And the other one is Mildred Dresselhaus, very, very wonderful, both symmetry fans. So yeah. Thank you.
Great. Vangelos. They're all my equivariants. And another equivariant. May I? No.
Very nice to see you in the afternoon.
May I ask one question? I'm just. I actually saw your presentation several times.
Where did you?
In the YouTube. No, it was actually different. Well, like I usually deal with